I can't imagine being sad about any aspect of this prize. So I'm really just delighted to have some good news for 2020 and excited about talking about the work and thrilled to go to Stockholm in 2021.
Yeah, you just have to be patient for that. Actually, as things turned out, the pandemic lingered on, and Andrea Ghez wouldn't get to visit Stockholm until 2022. We hope you'll check out her appearance at the upcoming Nobel Week Dialogue on December the 9th, on the theme of the future of life. But in the meantime, here's an encore presentation of our conversation with Andrea Ghez from Season 2.
At the center of galaxies, things become much more extreme in almost any way you can describe.
You're listening to Nobel Prize Conversations. That was 2020 physics laureate Andrea Ghez.
It's like a crowded urban center, so it's like downtown in a city. So you have a lot of stars that are packed together, and things move much more quickly at the center than they do out in the suburbs. So same thing, you think of urban centers as a fast-moving, fast-paced place.
Step by step, Andrea Ghez kept finding better ways to measure the speedy suns at the hub of our Milky Way galaxy. With enough data, she could eventually see the unseeable, the supermassive black hole that ruled these stars. For this discovery, she received the 2020 Nobel Prize in Physics, which she shared with Reinhard Genzel and Roger Penrose. Nobel Prize Conversations is produced with the support of our Nobel International partners, 3M, ABB, Ericsson and Scania. Your host is Adam Smith, Chief Scientific Officer at Nobel Prize Outreach. And now back to Andrea Ghez, who tells us what it's like to receive a Nobel Prize in 2020.
Yes, it is different because of COVID-19. Of course, I have never received it otherwise, so I don't really have a comparison point. But there's an interesting aspect of this, which is people are so happy to get good news. So I think there's been, it's added an interesting element in terms of how delighted people are to receive and share in good news. And then the ease in which it's possible to talk to people all around the world, to give interviews or to give talks and share the work, because everybody's new norm is to do it by the computer.
That's a good point. It must have changed things a bit, actually. It's made it more global, more easier to share.
It seems that way. I mean, it's been interesting in terms of thinking about all the invitations that have come in and how to think about what to do and what not to do, but realizing the huge range of people that can access you in this moment.
And another way it's strange this year is that, of course, you can't come to Stockholm. How does that feel?
Many people have asked how I feel, and I can't imagine being sad about any aspect of this prize. So I'm really just delighted to have some good news for 2020 and excited about talking about the work and thrilled to go to Stockholm in 2021.
Yeah, you just have to be patient for that. But I think patience is definitely one of your virtues. 25 years looking at the centre of the galaxy.
It's true. I always tell my students, just pay attention to the science. Everything will work out in the end.
Yeah, you're certainly a living example. Let's start there with that patience. Lots of words could be used. Confidence, optimism, stubbornness, about this long search for evidence for the supermassive black hole. What gave you the confidence to keep going?
Oh, actually, that's such an interesting question about how we thought about this work as we went along. We didn't set out to do a project that was 25 years long. In fact, we set out thinking that the project would be 3 years long, and we were only thinking of what has turned out to be the first phase, how to measure speeds or velocities. And even that, people were dubious about. So our first proposal was turned down. So at every stage, we've only thought about what's possible to do next. It's like the next step. And at each stage, I think we've been so delighted how well it's worked out that it leads you to the next step. So in a sense, it looks like a tremendous amount of patience. But in the process of doing it, we were only thinking about where you could go next. And then that led you to the next step. I don't know that anyone would have given us any telescope time had we told them that the whole thing would take us 25 years. So there's been a tremendous amount of progress along the way, which sort of fuels and motivates you to go on to the next step.
Andrea Ghez knew what kinds of measurements might prove her theory, but the problem was actually making those measurements. Problem number 1? Air. Even the thin air at the Keck Observatory, located on a remote Hawaiian volcano, created too much distortion to produce usable data. So how did Ghez overcome this? She incorporated a new technique that measured the distortion and then cancelled it out. Brand new at the time, adaptive optics enabled her to make observations with exceptional clarity. But this was just one of many challenges along the way.
The fundamental concept, though, that you want to go out looking for evidence of something that can't be seen is a difficult one to get one's head around. And to begin with, I think it's true to say that people didn't really think you'd be able to do what you set out to do, even looking at the trajectories of stars, the first part.
Well, it required new technology. So the first challenge was that people had to believe that at that point in time, the technology would actually work. So the ability to correct for the blurring effects of the Earth's atmosphere. So our first challenge, in a sense, was just to convince people that we could take a picture, never mind a time series. So I guess it does sound difficult to find something that you can't see, and yet the laws of physics tell you that this object should have great influence on things around it. So in fact, you expect to see a lot of motion if there are stars in the vicinity of this object. So in a sense, the challenge was really in being able to create the images and demonstrate that there were stars that were potentially very close to the black hole. And even seeing them close in 2 dimensions doesn't mean that they're close in 3 dimensions, because you're missing that third dimension when you just take an image.
I think it would be nice to describe what is going on at the place you're looking at, which is, 26,000 light years away. Tell us about the centre of the galaxy.
So the center of the galaxy is a really interesting place. At the center of galaxies, things become much more extreme in almost any way you can describe. So the density of stars goes up as you go towards the center of the galaxy. So it's a very crowded region. So in a sense, the analogy one can make, it's like a crowded urban center. So it's like downtown in a city. So you have a lot of stars that are packed together, and things move much more quickly at the center than they do out in the suburbs. So same thing, you think of urban centers as a fast-moving, fast-paced place. And other processes or other characteristics are also prevalent there. So there are strong magnetic fields. Any characteristic almost that you can think about in the galaxy are going to be more extreme at the center of the galaxy. So it's a very dynamic place.
And when you talk about the centre, do we mean the absolute geometrical centre of the galaxy? Is it possible to say what that is? Or?
Well, we believe this is the very center of the galaxy, but even such a question of where is the exact center is a very difficult thing to establish. So, in fact, we use these other measures first to think about where the center is, like where the density gets to be the highest. But in fact, where we pointed the telescope was at an unusual radio source. whose name is Sagittarius A star. It's a lousy name. Part of it's good. Sagittarius means that it's in the constellation of Sagittarius, which is the teapot, and the teapot pours into the center of the galaxy. So if you look up at the night sky, that helps you guide your eye to where the center of the galaxy is. But this radio source emits unlike any stars or gas that we typically think about. So when it was discovered, people gave it the name Sagittarius A because it was a very bright object, well, bright for the region, and asterisks because nuclear physicists use that notation to note excited state. So in fact, what they were trying to imply is that it's not a star, it's an excited gas state, and yet we call it Sagittarius A star. So it's really Sagittarius A, not a star. So we were really looking in the vicinity of this object because it had been suggested that its unusual emission was associated with matter falling onto a black hole, but at a very, very, very low rate.
So you have your supermassive black hole, and these had been observed in galaxies. Well, something had been observed in galaxies elsewhere in the universe, which indicated that there might be supermassive black holes. And the thinking is that one of these is at the center of every galaxy?
Yeah, so the evolution of our thinking about supermassive black holes was actually quite different than how we came to think about their counterparts, their lower mass counterparts, the stellar mass black holes. So the stellar mass black holes were thought of from a theoretical perspective initially, and then found observationally later on. The supermassive black holes were initially thought of because of observations of a small set of galaxies known as active galactic nuclei. And these galaxies, I often like to call them the prima donnas of the galaxy world because they're kind of show-offs. They have these huge jets of emission coming out from their centers. And at their center, they have emission that doesn't look like starlight, and it's very bright. So people hypothesize that this is from supermassive black holes. So a very large mass, millions to a billion times the mass of the sun, that was driving this unusual phenomena. And that led people to think, well, maybe all galaxies harbor supermassive black holes at their centers, but these are black holes that are quiet, or often I like to say they're black holes on a diet, simply because they're not accreting a lot of matter compared to the active galactic nuclei. And that is really what led us to think about looking for a supermassive black hole at the center of our own galaxy. Because if you're going to look for a typical, ordinary garden variety, absolutely nothing special about us. It's our own galaxy. And of course, it's the closest center of a galaxy that you'll ever have to study.
What's it doing there? What's it doing at the center of the galaxy? Is it a necessary part of the fact that the galaxy exists?
That's such an interesting question. And in fact, the way we think about the relationship between supermassive black holes and their host galaxies have evolved tremendously over the last 25 years. So when we first started to report our results, in some sense, the first phase, the thinking was very different. It was, which came first? Did the black hole come first, or did the galaxy come first? This is very much like the chicken or the egg problem, which came first. And we had theories to explain both ideas. You could generate one before the other by different methods or ideas. But what has emerged since that time is that if you look at the candidate supermassive black holes in other galaxies, the mass of these galaxies corresponds very well to the mass of the black hole. In other words, the central component. So overall, it appears that the supermassive black holes are always roughly 0.1% of the mass of the central part of the galaxy. And this is a really interesting correlation because it's really hard to imagine a scenario in which something so small influences something so large. And so that leads us to the conclusion that whatever formed one had to form the other synergistically, that they had to form as together in a symbiotic relationship, and that there's some feedback that helps these two things maintain their relationship as both of them grow over time. So we've discovered that it's not the right question, which came first, that they actually came together, which means that supermassive black holes are an important element in terms of understanding the formation and evolution of galaxies.
And so the reason you were able to detect it was down to the motion of the stars that are surrounding it. And in particular, there's this one star, I think you've described as your favourite star in the universe.
Yes, my favorite star in the universe, indeed, is SO2. We've discovered thousands of stars at the center of the galaxy, so you have to figure out how to give them names. So S actually stands for Sagittarius A stars, and the first number tells you how close in rings the star is from the black hole. So 0 means it's in the closest, it's in the central region. And then we just number them in the order of discovery. Actually, we numbered them in order of proximity to where we thought the black hole was at the time of discovery. So that tells you that actually at the time we discovered the stars, there was a closer one, SO1. And we didn't know, in a sense, which one would win the race in terms of being the most interesting star. But it turns out that SO2, at the time of discovery, was at its furthest approach from the black hole. So very quickly, because what we've discovered is that it's on an orbit that has a very short orbital period. In other words, it takes 16 years to go all the way around. So while we might think 16 years to go all the way around, that seems like an awfully long time. Like if you put it in context with other things in our galaxy, it takes our sun 200 million years to go around the center of the galaxy. There's absolutely no hope of measuring the full orbit. And it's only because there's a very massive object that the orbital timescales can get down to a human or a career or an experiment's worth of time. So SO2 going around every 16 years made it the most powerful star. In fact, I should say, actually, it's not just that it's a short orbital period, but that we can get both images of this object and spectra. And spectra are super important because the images provide us with the motion in the plane of the sky, so the 2 dimensions, and we're missing how it moves along our line of sight. And this other technique of spectroscopy allows us to measure the star's motion along this line of sight. So this is the star with the shortest orbital period that's bright enough for us to get both images and spectra of the star.
You've painted a lovely picture of being able to see, yes, the 16-year orbit in 3 dimensions. Yes, you must feel a great connection with SO2. And rather sorry for SO1, rather missed out on the fame.
Well, poor SO1. It's actually important in the sense that it helps us, but it becomes an assistant. It's a sous chef rather than the chef. And it's having something that goes around in 16 years is sort of interesting in terms of your relationship, actually, because I can think of, as the star goes around, I can think of the key things that were happening to me as a human being, you know, when I got hired, when I got tenure, when I had kids. You know, it's slow enough that you can really think about what's happening as the star is going through its journey. And because it's elliptical, not a circle, the way it moves actually changes quite a bit. So when the star is at closest approach, it goes much faster than when it's at furthest approach. So things are very active. And in fact, that's an important point because you're much closer to the by definition, you're much closer to the black hole at closest approach. But that means also that you're deeper in the gravitational potential well, or rather, you're seeing more of the effects of stronger gravity. So you can actually test how Einstein predicts that space and time should mix as you get closer and closer to a strongly gravitating source.
Mm-hmm. I might be taking the connection between you and SO2 too far, but have you noticed any correlation between the activity of your own life and the speed with which the orbit is occurring? How connected are you?
Because that's such an interesting point where the physics, new physics is revealed, the energy that we put into this experiment goes way, way up. So I would say the activity of the group, the excitement of the group, and maybe the stress goes way up at closest approach. But there's actually a second test that becomes much more detectable. Well, it's detectable as you measure the difference between what happens at closest approach to furthest approach. This goes around every 16 years, so that's a 8-year period. So it's a slower process, but we are sort of heading into the next phase where we're starting to see this next signal emerge. And I'd have to say that's also the really exciting and nice thing about this is that you go from one thing where you see it clearly and you have enough time to think about it, digest it, develop the code, write the papers, and then you go into the next phase. Yeah, so it's exciting. It never ceases to amaze me how much information this star has to offer.
You've painted a beautiful picture again of this time of how there's sort of dynamic changes in what's happening in your observation. So when one talks about a 25-year sort of search, that sounds a bit even, but it's obviously not even at all. There are lots of highs and lows and all sorts of excitements along the way.
Yes, this SO2 definitely defines the pace of the work of understanding what's at the center of the galaxy from a gravitational physics point of view. But the other thing that's been so lovely about this project is that as technology has evolved, and there's been a rapid development in the ways in which we can see the center of the galaxy with this work, our ability to get sharp images from these large ground-based telescopes, it's unveiled things that we didn't expect near the black hole. So in a sense, we've had the opportunity to look at lots of different kinds of astrophysics that we didn't expect to be engaged with. So it was the gravitational physics that sort of drove and defined the measurements, but many new branches have emerged, which in a sense also have been a wonderful thing to investigate as SO2 is in its quieter phase, or not quieter, but, where you just have to be patient.
Andrea Ghez is the 4th woman to receive the Nobel Prize in Physics. She joins the ranks of remarkable scientists like Donna Strickland, Maria Guppert-Meyer, and Marie Curie. For the young Ghez, books about Curie and other leading women were a source of fascination. Today, she clearly understands the value of her visibility and how it sends a signal to the next generation.
You, as a successful female scientist, are a role model in, many ways. At least 2 ways are that you're a female physicist and a female Nobel laureate in physics, of which there are very few, of course. And you're also a scientist, and at this particular time, scientists in general are kind of needed, I would say. I mean, we're all very well aware of the spread of misinformation and the difficulties in evidence-based decision-making. How do you view your role as a role model?
I think this is, I take this very seriously, actually. I think that with a prize like this, there's great opportunity, but there's also great responsibility that comes with it, because you have the responsibility to share your science and the importance of science. At this moment in particular, encouraging the next generation to think critically and to talk about how one goes through that critical thinking process. These days in particular, the importance of discussion, the importance of disagreement, that's in fact how you get to a deeper understanding is actually when you don't agree with somebody else. So rather than shying away from difficult conversations where you have different perspectives, you can actually lean into that disagreement and learn something. So I think it's an important time to talk about the scientific process. It is that process of critical thinking and critiquing of each other's work. I mean, that's how science works, is we poke. So in a sense, I feel very strongly about talking about this process to the next generation. And then, of course, in terms of the gender role model, I've always felt very strongly about this, having been educated at institutions that don't have a lot of women or didn't have a lot of women. When I was a student, I really came to realize how important visible role models are, in the sense that they can show you the path, that path is possible. So in fact, I've always enjoyed and tried to teach at the introductory undergraduate level, because I think that standing up in front of a class and showing your enthusiasm and your presence is actually some of the most straightforward ways you can influence the next generation. So in that same way, I think this receiving the Nobel Prize gives me the opportunity to talk about and highlight the work. And that's interesting and important, not only because I think the work is interesting, but because I think it's so important that the next generation understands that there's a path forward for the young women as well as the young men.
When do you think it might become unremarkable that a female receives the physics Nobel Prize?
Oh, well, I think we're seeing tremendous progress. If you think about even hiring a female physicist in faculty. So I think I was the 4th female faculty hire at UCLA. So evidently number 4 is my number. But there are many more faculty already, and we can see the impact. I mean, in some sense, it's a trickle-down effect that the more faculty you have, the more students that come along at each level down. So the graduate students and then the undergraduates. So we already are seeing the change. It's slow but steady. The older I get, the more opportunities I have to understand the complexity of this dynamic. So it is certainly true that if you want to see more women considered, one of the best way to do that is to ask other women for their recommendation, simply because we tend to be very aware of our own communities. I mean, it's a bias that's very hard to overcome. So in a sense that if we only ask the guys who they think about, you're more likely to get a bunch of guys recommended. So to be conscious of our underlying and very natural, it's how we survive, biases. So the more we understand that if we want a diverse population of faculty, when we think about faculty hiring, that we have to ask a diverse set of people for recommendations. I mean, the more that we're conscious of what it takes to understand who's good and out there, how to tap into those networks, the better off we'll be. So I guess that's been my approach to trying to increase, at least at that level, faculty diversity. Understand that you have to ask a diverse group. Understand that if you want diverse points of view, you need diverse committees, and it will come naturally. I mean, for instance, because I care a lot about this issue, I tend to pay attention to the young women coming up. So I have an implicit bias. So if you ask me who's good, I'll be more aware of the really talented women. It's not that I don't pay attention to what's happening with the younger men, but I'm just attuned to the young women. I think it's a natural bias.
But it is interesting. You just see it all the time. We are all constrained by our own worldview, and to step outside it is not easy, I don't think.
Yes, social change is hard. And I'm excited, in a sense, I'm excited it amazes me to be still part of that, in a sense, the frontier of that change. So to be both as a scientist, part of the frontier of our changing knowledge, but it's almost like it's a different frontier. It's a frontier of our changing understanding of who can be a scientist. But, the Nobel Prize is amazing in the sense that, the first woman to win the Nobel Prize in physics was Marie Curie. I mean, she was just a phenomenal scientist, and to have her recognized so early on, I think is remarkable. And for me, she was an important role model. When I was young, my dad used to buy me books of leading women, and Marie Curie's biographies were some of the ones that I found most fascinating. So I really appreciate how much strong role models can make a difference.
As a young girl, did you know that you wanted to be a scientist?
Hindsight is 2020. So no. I mean, I was 4 when the moon landings first happened, and they clearly were a pivotal moment for me and many, many other people.
Do you remember them?
Vividly. And the family lore is that I said I wanted to be the first woman on the moon. So that I think that probably tells you more about my family than anything else. But it got me thinking about the universe. So my parents bought me a little telescope. And certainly it's what led to me pondering. I mean, what got me so interested was these conceptual problems of what do you mean the edge of the universe, the boundary problems, basically, the beginning of time, the end of time, the edge of the universe, these things that, you can't talk about. The way, one thinks as a kid about based on your own experience just leads you immediately to these contradictions. And I do remember this is what kept me up at night. It really bothered me. So there was something about it that really engaged me. Although at the same time, I wanted to drop out of school and be a dancer. And this is when I was very, very young. But it became very clear that I really enjoyed math. So math and logic puzzles and puzzles in general. So I had an aptitude for that kind of analytic thinking. So by the time I was in high school, it was very clear that math and science, I didn't understand within that, except for the fact that the things that really engaged me were the universe questions.
But I think it's interesting that you didn't accept necessarily statements like the edge of the universe. I mean, yes, people question it, but to really worry about it shows a questioning nature and a desire to really know, because it's so easy when you're receiving science at school just to learn the fact and accept it and not ask about it. And maybe that's the problem with science teaching, that it sort of turns into facts rather than questions.
Well, it's interesting that you point that out, because I went to a school that was all about asking questions and not teaching facts. So it was it was the University of Chicago's lab school. So it was developed by John Dewey, who was an educator who really believed in teaching people to learn rather than teaching people the facts. So I am certainly a product of an educational model that is all about teaching people to think. So in fact, it was just last night I gave a talk to the lab school at UCLA. His graduate student came out to UCLA and started the UCLA lab school. So I wanted my kids to go to this school, this elementary school, because I really believe so strongly in the importance of teaching people to think. The facts will change, but if you teach people to question, which is ultimately what we need to do as basic scientists, and actually as people, we need to question the world in which we live. It's coming back to this question of, critical thinking that's so critical at this moment. Yeah, I was fortunate. So I was fortunate to be educated in this manner.
Well, it obviously worked for you. I suppose the insecurities in most people that things like maths scare people a bit. So to enjoy maths and to enjoy using it is a place that most people don't quite get to, because they can relate it to a time at school when they kind of failed to measure up quite as much as they should have, which is a terrible thing that school does to people.
For me, I think math is my language. It's a language of logic, of if A, then B. And for me, it's interesting because for me, the things that scared me or put me off were actually writing and speaking. So the fact that I enjoy speaking to public audiences today is my surprise. That in fact, those were the things that terrified me far more than math.
When did you suddenly discover that you were no longer worried by that?
Oh, gosh, that's actually a funny story. Well, funny to me. It's ironic. It's a reminder that we should always explore the things that we were a little afraid of. So when I applied to graduate school, I actually applied, I wanted to go someplace that wouldn't force me to be a teaching assistant because I was so concerned about public speaking. I was just horrified by it. So I was one of those people who, if you asked me my name, I would, I'd get very nervous in a circle. So I went to Caltech, where I had a research assistantship. I had to give my first research talk, a lunch series, and I shook from my head to my toe. And my advisor said, "You need to teach." So I think this remembering back on these moments, actually, I kind of can't believe how this actually unfolded, because I thought, okay, I have to teach, but I don't want to do it. But then I thought, okay, I'm going to teach the introductory level because there's so few women at Caltech. This is the class I really want to teach. And at Caltech, professors are the ones who get to do those discussion sections. So I actually had to argue with the department person who was in charge of this that they should let me do this. So I took somehow something that I was just terrified to do, and I made it about something I really wanted to do, which because I was already interested and quite aware, having been an undergrad at MIT and then a grad student at Caltech, about the dearth of women. So I ended up doing a teaching assistantship at the introductory level, and you just can't get nervous that often. So I just had to get over it. So it was an interesting year of learning that, if you can find the reason you want to do it, you can surmount your fear of doing it. So I think I learned to translate nervousness into excitement, because what I wanted to share with the students is, that this isn't that hard.
No, and I suppose, yes, in the sort of teaching tradition of Caltech and that sort of Feynman tradition, played exactly to your strengths. It's asking questions, it's probing, it's doing what you believe in. And so why be nervous about being yourself, if you see what I mean? I don't know.
It took some time. So I'm really grateful for that experience, because it really showed me that it was something that, in spite of my early fears, that I had the capacity to do. And so I really like to encourage my students and my kids, figure out what you enjoy doing, but always keep trying new things, because you don't know without trying what you'll ultimately enjoy.
So sometimes when you ask, especially a recent laureate, the question, so what's next? They just look at you with horror and say, was that not enough for you? But in your case, I think what's next is probably quite relevant. What's going on right now?
Oh gosh, there's so much that we're in the midst of doing. I mean, the center of the galaxy is such a rich and exciting place, and this is a project that just gets more and more interesting with time. So you're really benefited from continuing further on. So we're in the middle of these next tests of how gravity works near a supermassive black hole. And then pursuing so many of these questions that have emerged from the center of the galaxy in terms of what we expect to see in the vicinity. One of my favorite ones is trying to understand these objects that appear to be what we call tidally disruptive. In other words, the outer layers are being stripped off as they make their closest approach to the black hole. And I think it might be revealing processes that might give us new insight into what's being seen with the gravitational wave detectors. So in other words, there's a mystery that's being unveiled with our new window into the universe that may help us understand another mystery that's being struggled with a different window into the universe. So it's like these pieces of the puzzle that we're putting together. And then moving forward, we're working on advancing the technologies that we're using at the Keck telescope to get even clearer pictures. And then ultimately, I'm part of the 30-meter telescope, which is the next generation of telescopes. So I'm thrilled about this prize, but I'm also just so excited about the future of this work.
It sounds like I can't see, with all that to do, you're going to have time to be a role model at the same time, or rather an active role model out there talking to people, but I guess you'll fit it all in somehow.
Well, actually, the thing I like to say is, figure out what you want to do, figure out, the new things, but also figure out how to help others enjoy and discover what they like to do. So I like to think of it actually in thirds. And I think so much of what our responsibility as scientists is to go out and talk about our research, that public engagement in science. And I think that in my case, can have the dual purpose of public engagement and the encouragement of the next generation of young women.
You've just heard Nobel Prize Conversations, a podcast series with Adam Smith by Filt Hinterland for Nobel Prize Outreach. The producer for this episode was Sally Henriksen, and I'm Claire Brilliant. Music by Epidemic Sound. This episode is from season 2 of the show. You can find previous seasons and conversations on Acast or wherever you listen to podcasts. Thanks for listening.